Hello, this is Jude Socrates and welcome to today's video where we'll be talking about matrix multiplication. We are going to have a couple of items on our agenda. We will learn how to multiply a matrix by a vector, and we're going to use this to rewrite a system of equations. So we will see what is called the matrix product form for a system of equations. Okay, so first we have to set up our scenario. We start with an m by n matrix, let's call that A, and we have a vector x from our n, okay? So notice that n is the number of columns of our n by n matrix. So our goal is to define the matrix product 8 times x. How are we going to do that? So the first thing we're going to do is we will turn x into a column matrix, right? So it starts out as a vector, x1 to xn, but instead of writing it down horizontally, we write it down vertically. Okay, so that is now a column matrix, an n by 1 column matrix. What about A? We are going to partition A into n columns. So we're going to write that as A equals column 1, column 2, up to column n, where each column C sub I is an m by 1 matrix. So with that set up now, we are ready to define our matrix product. So again, A is made of columns 1 through n, an m by n matrix. X is from Rn. We are going to define 8 times x. So what is 8 times x? Here is the matrix A. Here is x turned into a column matrix. It is simply a linear combination of the columns of A using the coefficients in x. So to C1, we will multiply by x1. That's our first term. To C2, we will multiply by x2. That's our second term. Keep going, make that linear combination, add it all together. That is the matrix product, 8 times x. Now, something a little bit funny happens. We mentioned that each column is an m by 1 matrix. So we start out with an n by 1 matrix for x, but when we create the product, we get an m by 1 matrix, not n by 1. That throws off a lot of people the first time we see this. So it is also important that the number of coefficients in x matches the number of columns in A, because we need one coefficient for each column of A. Okay, so here's our example. We have a 3 by 4 matrix, and x is a 4 by 1 column matrix. Okay, so I've already gone ahead and wrote x as a 4 by 1 column matrix, even though it starts out as a vector from R4. So we take column 1 of A and multiply it by -3. So let's put our coefficient -3 down here, and we multiply by column 1. Okay, so let's copy column 1 over there. And then next we have 10, our next coefficient. So let's copy that down here. Multiply by column 2. Okay, keep going. -9, multiply by column 3, and then +2, multiply by column 4. Okay, so that is our setup, and now we're going to do the arithmetic. Okay, so I hope we don't make any mistakes here. Let's see, so -3 times this vector, we will get +6, -6, and +9. Okay, next we have 10 times this vector. So we will have 30, -10, and 70. So that's easy. -9 times this vector. So I'm going to put a plus on the outside and multiply the vector by -9. So we have -45 positive 27 and negative 81. Okay, and finally, we will multiply the last column by 2. We get 10 minus 14 and minus 6. Okay, I hope that's correct. So we add it all together, and let's see, let me make a copy of this. Let's see, 40 minus 45, negative 5 plus 6. I believe that's positive 1. And then what do we have here? Let's see, that's negative 24 plus 27 is positive 3 minus 6. I think that's negative 3. And then let's see, 79 minus 81, negative 2 minus 6. I believe that's negative 8. Okay, so this is our matrix product. Okay, so we can write that 8 times x is equal to this matrix, and it's going to scroll when I copy that in. There we go. That is our matrix product, 8 times x. Now, you've seen me many times use Maple to do our computations for us. So, of course, we have a computational algorithm built into Maple. All I have to do is press the equal sign over here, and it understands that it's supposed to perform the matrix product. So we confirm that we did not make any silly arithmetic mistakes in our computation. Okay, now in your homework, you are going to do a couple of easy proofs. You're going to prove the 2 basic properties of matrix multiplication. So if you're given an m by n matrix A and 2 vectors x and y from Rn and a scalar k, you have the additivity property. A multiplied by the quantity x plus y is the same as a times x plus a times y. So that looks a lot like the distributive property, don't you think? And we also have the homogeneity property, where a times the quantity k times x, that's a scalar product, is k times a times x. Okay, so this a times x is a matrix product. And then when you multiply by k, that becomes a scalar product. So all you have to do is use the definition of what a matrix product is and the properties of linear combinations that we saw in section 1.1. Now, I didn't put this on our agenda, but I thought let's get a little sneak preview of how to multiply 2 matrices in general. Okay, so the general scenario is you're given 2 matrices, but you can't just multiply them. They have to satisfy what's called a compatibility requirement. So we already saw that if you have a times x, then the number of components in x must be the same as the number of columns in A. So that generalizes to a bigger matrix B instead of just 1 column. So the requirement is that the number of columns in A, which is k in this notation, must be the number of rows in B, which is in this notation. Okay? So all you have to do is repeat what we just did to every column of B. So we did this in our last example. It's the same matrix A. So all we have to do is repeat the process for column 2. Okay, so I copied our work in our last exercise. This was the answer that we got for column 1. So we repeat the process with A on the left and column 2 on the right. Okay, so to save time, let's just ask Maple to do the work for us. And that's our answer. Ooh, we probably would have made a mistake or 2 there. Okay, let's see if we can check that mentally. Okay, we're going to multiply column 1 by 6, column 2 by 0, so that just goes away, column 3 by minus 5, column 4 by minus 8. Okay, so let's see how to get the first entry. minus 77. So negative 2 gets multiplied to 6, so we get negative 12. Column 2 doesn't contribute. 5 gets multiplied by minus 5, so minus 12 minus 25. So right now we have minus 37. And then the last column gets multiplied by minus 8. So 5 gets multiplied by minus 8. That's minus 40. So minus 37 minus 40, we get minus 77. So that is, of course, correct. And the answer, A times B, is simply these two columns put together. So A times B is just the matrix where this is in column 1 and this is in column 2. Okay, so of course we're going to see this later on in chapter 3. And in fact, we're going to backtrack a little bit. We're starting out with multiplying two matrices. How about addition and subtraction? So we're going to see those operations as well. So for the second item in our agenda, we said that we're going to see another way, an alternative way by which we can write down a linear system of equations. So this is called the matrix product form of a linear system. So how do we do that? Well, here was our example. We multiplied this matrix by this column matrix, and this was our answer. So what we're going to do is we're just going to turn this vector minus 3, 10, minus 9, 2 back to variables. Okay, so in fact, this was how we defined the matrix product, where we have the entries of x, and we have column 1, column 2, column 3, column 4. Okay, so let's do this in general. So we said that this product is just column 1 multiplied by x1. Okay, and then we have column 2 multiplied by x2, column 3 multiplied by x3, and finally column 4 multiplied by x4. All right, so that is our matrix product. All right, so let us expand this out. Let's copy it down here. We are going to multiply column 1 by x1. Oh, look, it's just cut and paste. Multiply column 2 by x2. So I'll make that minus x2, 7x2. And then x3 multiplied into column 3. x4 multiplied into column 4. All right, and then we are going to combine that all together into one column matrix. So we have minus 2x1 plus 3x2 plus 5x3 and plus 5x4. Okay, so that's the first entry, and I'm going to do the rest for us to save a little time. Okay, so in the second entry, we have 2x1 minus x2 minus 3x3 minus 7x4, negative 3x1 plus 7x2 plus 9x3 minus 3x4. But let's remind ourselves that this was part of this equation, okay? So what this means is that if you replace the x's by minus 3, 10, minus 9, 2, you will get this right-hand side. So I'm going to copy this right-hand side and put that over here, okay? So check it out. We have a 3 by 1 matrix on the left. This is all one number, okay? And that matrix is equal to this matrix. So of course, what that means is that this expression has to be equal to 1. And so on with those two other rows. So that second entry has to be equal to -3, and this third entry has to be equal to -8. Of course, that should look very familiar to you. That's a system of equations, linear equations. We have 3 equations in 4 variables. So we are back to, what was that? Section 1.3. Okay, so we now have 3 ways by which we can write down a system of linear equations. So this was the same system that we just got, but I wrote it out so that the components are nicely aligned. And that came from this matrix product form for a linear system. Now, of course, if we actually want to solve this system, we still have to put it into augmented matrix form. So you might think, well, what did we do all of that for if we just have to go back to the old way? We are going to see this, of course, in chapter 2, and we will see how this notation is going to help us simplify our theorems, our statements, our equations. Okay, so if we want to solve this system, then we just have to make a copy of this. So let's write down our system, remove the vertical bars as usual, and then compute matrices REF. Okay, so do we pass the inconsistency test? There is no 0 equals 1, so our system is consistent. Excellent. Where are our leading ones? They're right here, column 1, column 2, column 3. So x1, x2, and x3 are free. x1, x2, and x3 are leading, and x4 is free. So let's write that down. Our leading variables are x1, x2, and x3. So let's make it official. 3 leading variables, and we have 1 free variable, which is x4. Okay, so let's write down the equations corresponding to these 3 rows. So we have x1 plus 4x4 is equal to 5, and x2 minus 9x4 equals -8, and the last row, x3 plus 8x4 equals 7. All right, and our x4 is of course free, so we are ready to write down our solution vector. Solve for x1. Okay, so it's relatively simple. We just move the 4x4 to the other side. So x1 is 5 minus 4x4. x2 is -8 plus 9x4. x3 is 7 minus 8x4. And x4 is our free variable, so we just put x4 there. There we go. And of course, x4 is any real number. All right, there you go. So we have a new way to write down a system of equations, ax equals b. But for now, we have to use the augmented matrix to solve our system. So maybe spoiler alert, when we get to square matrices, we will see another way to solve a system of equations using what's called the inverse of a matrix. So when you multiply 2 numbers and you want to do the opposite operation, you divide. But we don't say you divide by a matrix, we say you multiply by the matrix inverse. So that's something to look forward to in chapter 3. Okay, so we have reached the end of this video. And once again, I thank you for watching. and I hope to see you next time. Enjoy the rest of your day.